So we are doing lecture 14, and this is just the continuation of the state machines. Okay. What we have seen so far is these sequence detectors, simple, easy sequence detectors, and we see the procedure for design of everything. But then there may be situations where you have, instead of one input, you have two inputs. Instead of one output, you have several outputs, and so on. Remember when we just started with the state machines, we said that sequence detectors are good representation of very general controllers. One input, one output, but every controller really looks very similar to these sequence detectors. I still say the same thing, except that it's not a bad idea to see a little controller with or a little FSM with more than one input. I'm going to do this. I'm going to design a circuit, and I'm calling this circuit, let's say, a residue. I think residue is RE. Residue 5 circuit. And it has two inputs, let's say A1, A0, and then it has three outputs, which are the remainder or the residues, R2, R1, R0. And then, as always, it has a clock and it has a reset. And this circuit works continuously, and as data come in, it calculates the total binary number that has been received, total number, binary number in 2-bit segments coming in, and it adds them up, and then whatever has been calculated, it calculates the remainder of that total number accumulated so far by 5. What it means is, let's say my A1, A0 starts with 0, 0. Then it becomes, let's say this is the clock, by the way. Okay. So on the first clock, on the second clock, on the third clock, fourth clock, and so on. And let's say I'm doing rising edge. I have 0, 0. Let's say this has changed to 1, 0. Then somewhere along here it changes to 1, 1. Somewhere along here it changes to, let's give it one more pulse or two more pulses. I still have a space on the right side, and 1, 0 continues 1, 0, 0, 0. All right. At this point, the total number I have received on A is 0. At this point, the total number I received on A is 0 plus 2, which is 2. At this point, total number I received on A is 2 plus 3 is 5. Okay, and the remainder of 5 divided by 5 is 0, and therefore R2, R1, R0, it is 0 so far. By this time it changes to 2. By this time it changes to, see, 2 plus 3 is 5 is 0, so the remainder is 0. Then in here the remainder is 0, and then I have a 2 added to it, and 2 added to 0 is 2, so the remainder by 5 is 2. And how about this part? I'm still adding another 2, and therefore the remainder by 5 becomes 4. And then I'm adding another 0, so the remainder by 5 doesn't change and remains 4. Okay? So at any point in time you look at this and you find that the output is the total number of inputs ever received. Okay? The total value of the 2-bit numbers. So this is more correct as far as the functionality of the circuit is concerned. The total value of the 2-bit numbers ever received on A is calculated, divided by 5 continuously, and then the output becomes the remainder of that. Okay, if the problem description is clear, let's go with the design of it. Okay, any question on the problem description? Okay. All right, so let's do one more pulse here, and let's say at this point my input has changed to 1 0, and then I have 4 plus 2 added, and therefore what does my residue become? 1. Okay, see, 4 plus 2 divided by 5 is remainder is 1. Okay, so this should be pretty much a good representation or a good example for the behavior of this circuit. All right, let's do the design, and I have so it is the residue 5 circuit, and I start with a state diagram, and I have a state where my output is 0 0 0. Okay, actually I need 3 outputs because remainder by 5 is either 0, 1, 2, 3, or 4. Because it can go up to 4, I need 3 bits. Okay, I'm in state A, where the assumed total number is divisible by 5, and then I have 0, my remainder. For as long as I receive 0 0 on my A inputs, I go to the same state. Like, for example, look at this situation here. When I receive a 0 0, my residue doesn't change. My remainder doesn't change, obviously, because I'm adding whatever I had with 0 0. If I'm in this state and I receive a 0 1, then I go to state B. State B, the residue is 1, remainder is 1. Okay, if I'm in the A state and I receive 1 0, remainder becomes 2. If I'm in state A and then the input is 1 1, I go to state D, where I have 0 1 1. Okay. What else? Well, nothing else, because A1, A0 is a 2-bit number, and I'm not going to get anything other than that, other than the 4 cases that I've shown. And now let's go for each of these states. If I'm in state B, again 0 0 takes me back to this same state. 0 1, the remainder added to 1 becomes 2. 0 1 is my remainder in state B. Added 2 to it becomes the remainder becomes 3. Okay. 0, 1, or 1 is the remainder in state B, and what if I add a 3 to it? Remainder becomes 4. I guess you can more or less tell the rest of the states how they're gonna work. Alright, let's do state C. I'm gonna do some changes in my colors here. State C, again 0, 0, same state. 0, 1 adds 1 to it. Therefore, if the remainder is 2, adding a 1 to it makes it 3. If I'm in state C and 1, 0 is received, 1, 0 plus 1, 0, that's 4, and therefore I go to state E. And if 1, 1 is received, see, I have 1, 0, which is 2, 1, 1 is 3, added together is 5. What's the residue? Is 0. So I go back to state A. Okay, this was with state C. Let's do state D, for example. And D, again, 0, 0 takes me back to where I was. 0, 1 goes one step down. 1, 0. I have 1, 1, 1, 0. That's 2. And therefore, that goes back to state E. What if I receive 1, 1, 1, 1 plus 1, 1, that's 6. Okay, remainder is 1, so I go to state B. Okay, and this is state. All right. Let's do state E. 0, 0, as with the rest. Takes me back to state E. Then 0, 1. That's 4 plus 1 is 5. That takes me to state 0. 1, 0. I have 4 plus 2 is 6. That takes me to state B. 1, 1. That's 4 plus 1, 1 is I'm trying to find a way to state C. Okay, 4 plus 1, 1 is 6, so the remainder is 2. I have to go to state C, and I can either go, I think it's safer going this way. 1, 1. Alright, how many edges do I have out of each state? Because I have 2 inputs, I have 4 edges out of each state, as opposed to what I have been doing, which I had in the past. You saw that I had 2 inputs. I had 1 input, and therefore there were only 2 edges out. So that's the state machine. The outputs are there, and if I were to implement this with Carnot maps and all that, I would have 1, 2, 3, 4, 5 states requiring 3 state variables, 2 inputs requiring 5 variable Carnot maps for my so I would have 3, here it is, 3 5 variable Carnot maps for the state variables, and then I need only 1 Actually, I don't even need any Carnot maps for my outputs because I can set my state assignment the same as my outputs, and therefore what comes out of my state assignment is what comes out of my three states is already the output, so I don't really have to worry about having more hardware for my outputs. If you like to, though, you can, and it turns out that each output is the same as one of the state variables. One of the states. So the three outputs will be directly taken from the three flip-flops of your states. All right, that's if you want to do Carnot map, which is not what I want to do. I'm going to do a little bit of painting here. See, this is the state E. State D is this one here. So the edges out of that is it can be seen easily. Then the problem is with the state C. Let me see how my black highlighter is gonna work. Not good, huh? No, not bad. I see very good here. I see actually. So let me. I am seeing something. Okay. Anyway, trust me, there is C010 written there. Okay. And then I have state B where okay, and then I have state A, which I'm not coloring. All right. So I have 4 states with 4 colors, and this is how things are set up. And how do we design it now? Okay, to do the design, I'm going to be using one hot. Okay, instead of doing Carnot maps, I'm going to be doing one hot. And so let's go on to the next slide. I have 1, 2, 3, 4, 5 flip-flops, and therefore 5 states, and therefore I need 5 flip-flops. And so I'm gonna go here and do a flip-flop for state A. Now all of them, they have the same clock and they have the same reset. 2, 3, 4, 5. Okay, gonna do the clock and reset. And once again, let's assume it is asynchronous. Reset. This clock. This is reset. This output, the first one is the output corresponding to state A, second one corresponding to state B, third one corresponding to state C, state D, and state E. Okay? Now, see, if I had done the binary mapping, meaning that I had 3 flip-flops, I could make the output of the flip-flops the same as the state variable, so I wouldn't need any logic for the output. In this case, though, this is not the situation, and therefore I do need some extra logic for my outputs, which we will be seeing in a few minutes. All right. What do I have here? I have 2 inputs, and my 2 inputs are A1, A0. Okay. Of each state, I have 4 edges or 4 outputs. Okay. So what I do is, if you go back and look at the one-hot machines that we did before, the one-hot machines, they had this flip-flop, and then the output of that was a circuit like this, right? The input came in and made 2 branches. Okay, in effect, this little hardware is a 1 to 2 decoder, with this input being the flip-flop output, which goes to the input of that. See, just clear it, make this a little bit more clear. See, this is a 1 to 2 decoder, okay, with this acting as the enable, and this being the single input data. What I'm trying to do now is just expand the same idea for this problem and say, well, all I need is what? I need a 2 to 4 decoder. We have already seen decoders. And bring in the flip-flop output here and make that as the enable input of the make that the enable input of the decoder. So what I have here is a decoder here, a decoder here, a decoder here, a decoder here, and one right over here. This becomes the enable for each of the decoders. And then over here, D, C, D, D, C, D. These are 2 to 4 binary decoders, active high enable, active high outputs. Okay. Now, each of these flip-flops has an OR gate, but then I'm going to distance the OR gate a little from the input so that later on I put my resetting hardware in here. Now you see why I did all those colorings in the previous one. State A is the yellow state, and then there are 4 edges out of that. 1, 2, 3, 4 for 0, 0, 0, 1, 1, 1, 1, 0. 0, 0 takes me back to the same state. Zero, 1 takes me forward. 1, 0 takes me here, and 1, 1 takes me, you'll be seeing a lot of lines being drawn. Takes me there. Okay, let's do the highlighting. State A is the yellow state, and this is one line coming out of it. This is the next one. This one is the third one, and this one is the fourth line coming out of it. Okay, then we are talking about the state B, which is the red state. And state B, 0, 0 goes back to the same state. 0, 1 goes forward. 1, 0 goes next one over, and then 1, 1 goes here. Then I'm doing state C. State C, 0, 0 takes me back to where I was. Zero, 1 takes me for right. 0, 1 takes me next state. One, 0. Okay, C is what? C is 0, 1, 0. So next one takes me. Wait, no, I made a mistake here. This one actually goes to state D. This one goes to state E. Okay, now let's do state D. State D, 0, 0 goes back to the same state. 0, 1 goes to this. 1, 0 goes all the way to state A. And then 1, 1 goes to state B. Then state E, state E, 0, 0 goes back to the same state. 0, 1 goes to A. 1, 0 goes to B. 1 1 goes to C. Okay. So this is the state C, which is the black one. This is state B, which is the red one. This one is the green one. And then this one is the blue one. All right. So this is the one hot implementation of this residue 5 circuit. Now what we need to do is to put the resetting and the outputs. Okay. The problem with the one hot is that you have to have the resetting, so that in this case I want to start with 0 0 0. Okay. I want to start with output 0 0 0 or state A. That means the same thing as I did before. I have to put a 1 in the first state and then 0 0 0 in the other states. So this is going to be my resetting. I put an AND gate here. This becomes my init input. Let's call it init and not reset. And this becomes the inverter. So if init is 1, I am initializing this. I'm sorry, this is going to be 1, so I have to put an OR gate. By the way, you can reuse the existing OR gate. Okay. If init is 1, I'm pushing a 1 into this. And then if init is 1, I am killing this. I am killing this, this, and this. Okay. So I bring in my init, put an inverter on it. Here. Here, here, and here. Okay, lots of lines. Hopefully they're correct, right? I mean, this is really the same as the state diagram, except that this is I guess if I had drawn it in a vertical fashion, that would probably be a little bit less lines or something. Anyway, but see here we don't have resetting. And finally, what I need to do is to create my outputs. Okay, I have 3 outputs. R2, R1, R0. I would probably not do the outputs. Oh, by the way, these are OR gates, not. R0 is 1. R0 is 1 when I'm in states B or D. R0 is 1 when I'm in states B or D. So this is the output. here, and this is state B. Okay, B or D. R1 is 1 when I am in state C or D. C or D. That's for R1. D is already here. And C is this. And finally, R2 is 1 when I am in state E only. And therefore, I don't really need an OR gate. But then since I have it, I'm going to just do this. That's a complete circuit. Okay? And instead of an AND gate with inverted input for the one input circuit, here I'm using a decoder. Let me also show you the details of the decoder. This is a decoder with enable, 2 inputs, 1, 0. This is the binary input. It has 4 active high outputs, so it is a 2 to 4 binary decoder with active high enable and active high outputs. Okay. Okay, that's my last example of state machines. This one, right? When